my own study as well, use first-order Markov chain models. They comprise other models. Finite state atoms can be simplified as Markov chain. N-grams are actually nth-order Markov chains. So you have probably already seen how a Markov chain is done. It's a bunch of states, probability of transition from a state to the other, and you can calculate very easily the probability of a sequence of states into a chain. It's very simple. You pick up all the states you traverse, you multiply the probabilities, and you obtain the conditional probability of the sequence. Well, the reverse problem is slightly more complex. Given a set of sequences, how do I train, how do I create the Markov chain which fits best this set of sequences? Well, usually you will do this with a maximum likelihood model. Basically, you would create the Markov chain in which the observed sequences have the maximum probability. So if I've seen A, B, C, and then I've seen A, B, C, D, and then I've seen A, B, C, D, E, and something else, I train the Markov model by choosing the parameters that make this bunch of sequences as likely as possible. This can be done simply or through a Bayesian calculation. The simple calculation is what you will do normally for training Markovian models. What can be discovered in a very brief time if you try to experiment with this is that if you have null probabilities, so if you have transitions that have never been observed, they will be transitions without an arc in your resulting Markov model. This can be deleterious for your anomaly detection system because if you have a training set which does not show a particular transition, and then at some point this transition shows up, you will have a zero probability sequence, and so an immediate flag of anomaly, while it may be a normal condition for some reason. So there's another problem, which is the fact that if you pick up one of these sequences and you just try to compute the probability for a short sequence and then for a long sequence, obviously the probability for the long sequence will be lower than the probability for the short sequence because you traverse more than one arc which has a weight which is lower than 1. So every time you add a letter, every time you add a state to the sequence, you will invariably lower the probability. There are some mathematical tricks here to smooth this probability. I wrote a paper which has been published in a congress in Turkey, which is called Behavioral Intrusion Detection. If you look it up on the internet or on my webpage, you will find it, and it has all the mathematics you may want to explain this trick. But basically, what happens is that you need a Bayesian calculation to compute the probabilities, and as maybe you already know, in Bayesian calculation, there's a well-known problem, which is the problem of determining the so-called prior probability. And in that paper, I find out a prior probability for such a model. Well, you may have heard talking of hidden Markov models. What's a hidden Markov model? It's a Markov model where we do not really see the states. So I don't see the ACGT state in the previous example, but I see something which is generated from the state, so a function of the states. it's hidden because I don't see directly the state. I see the function of the state. This adds up complexity in order to find out how likely is a sequence in a given HMM. There's an algorithm which is called the forward algorithm, which can be used. And when you try to determine which is the most probable path that can have generated a sequence, this is a mathematically complex problem which has been solved by an Italian named Viterbi. And the Viterbi algorithm is very well known. It's used in your regular GSM cell phones, for example. And there's another algorithm, which is the one we could be interested in. It's how to learn the parameters of an hidden Markov model from the sequences. And I won't go into the detail, but it's sufficient to know that there's an algorithm called forward-backward or Bloom-Welch, which can compute this for you. So if you decide that you want to model your system calls with hidden Markov models, that's not a problem. You can, it's a bit more difficult than using your regular Markov models, but you can do that. Actually, from my experience and my opinion, it's not really necessary in the case of system calls, but results might vary. So I was talking before of syscall anomaly. What's syscall anomaly? It's a model proposed by Giovanni Vigna, where each system call is evaluated on 4 models. On each system call, on each parameter of the system call, a string length is computed, character distribution is computed, structure of the string is computed, and the parameter is evaluated to see if it's a token. These models are theoretically interesting, very interesting, but they are flawed. In real world, they do not work. So what we did was to analyze them. For instance, the structural inference model, which tries to characterize the structure of a string, is fundamentally a Markovian model without probabilities. What happens is that since they did not take into account the 0 probability problem, if you change just, if in your parameter appears a character that has never been there before, this is sufficient to make this particular model scream there's an anomaly. So since the syscall anomaly stuff automatically tries to understand if a model gives good results or bad results during training, what happens is that this model gets automatically tuned out because it generates too many false positives. So it's there, it's implemented, it's executed, but its results are discarded by the algorithm itself. The token search, again, you must predefine what is a token, so much for unsupervised learning. And again, you don't have probabilities. So if you have a token, which is, for example, a UID-GID combination, and there's a combination of UID and GIDs which you have never seen once, or you have seen, then it will be flagged as anomaly. But if you have a UID-GID combination that you've seen just once, while another UID-GID combination is seen 99% of the time, the seen once combination is not flagged as more anomalous than the other, which is not correct. So we evolved these models. We picked up the structural inference model and threw it away. As soon as we threw it away, false positives of the system halved, which is quite interesting. We implemented a model for file system paths because it's a file system is the most common parameter for which can be a string in a system call, and therefore it makes sense to have a model for this. We looked at structural similarities, so elements in common, /user /lib is more similar to /lib than to /opt/bin, for example, and the depth at which various elements are. We introduced a probabilistic model for token search, and we specialized it for UID and GID. Because if you think about it, when you see a UID-GID combination, what you're really interested in is it 0? Is it between 0 and 1,000? Or is it above 1,000? Because these are the three classes of UIDs and GIDs, for example, on Linux systems. What we added two things, basically. The first thing was to correlate the various arguments of a system call. What did we discover? For example, we discovered that the open syscall is being used for thousands of different reasons, in thousands of different ways. So it does not make sense to create a model, one model, for the open syscall. The open syscall will do whatever it wants. We create sub-models. We create models for subtypes of open system calls. And this gives us the possibility to create more stringent models which fit better and which are easier to deal with for flagging anomalies. And to do this, we used a hierarchical clustering algorithm. Basically, we merged similar uses of open until we, merging subsequent uses, created more damage than it solved. And this generated a very useful distinction among different ways to use the same syscall, which we used also in the step of correlation. We added a correlation of the sequence of the system calls, because Giovanni was interested in studying, and he gave the first root study of how to evaluate parameters. But he didn't add in a time correlation. We did. And we correlated over time, not looking just at the open or whatever else system call, but we correlated over time looking at the sub-model of the system call. And this gave us much better precision and much better results. So what's clustering? Clustering means grouping things together so that similar things are together and dissimilar things are not together. Looks like a very simple thing to do. For humans, it's very simple. For computers, it isn't. We used a hierarchical agglomerative algorithm, which means that it's an algorithm that picks up the objects, finds out the two objects that are most similar, merges them, then goes again and again until merging means merging two very different things. There's a stop criterion. At that point, the algorithm stops, and you have clusters of similar things merged together and dissimilar things not merged together.